A rocket launches with a tower of fire. The ground shakes, and thousands of kilograms of fuel vanish at terrifying speed. Even after that initial violence, the rocket is barely moving fast enough to reach its destination. We often focus on how far away space is, but the real barrier is the speedometer. Physics demand specific speeds. To stay in orbit, a spacecraft must move sideways at 7.8 kilometers per second. Escaping Earth's gravity entirely requires pushing past 11 kilometers per second. Every launch is a fight to cross these strict, unforgiving mathematical boundaries. The difficulty lies in propellant weight. A rocket must carry the fuel needed to accelerate the fuel itself. The fuel has to lift more fuel, which lifts more fuel, which lifts more fuel. The cycle compounds until the machine is almost entirely propellant. While an aircraft pulls oxygen from the atmosphere to burn its fuel, a rocket must carry its own heavy liquid oxidizer. This adds even more mass to the vehicle, worsening the weight problem before the engines even ignite. This makes the rocket a paradox of engineering, a massive, highly complex structure that exists mostly to carry its own propellant. In the late 1800s, Konstantin Tsiolkovsky derived the mathematics of this paradox while living in near isolation in Russia. He had no rockets to test, just equations. His work highlighted a unique physical challenge. Unlike cars that push against the ground, or even boats that push against water, a rocket in a vacuum has nothing to push against. To move forward in a void, you must throw mass backward. Imagine throwing a heavy ball while standing on a frictionless surface. You move in the opposite direction because momentum must balance. A rocket engine performs this at extreme scale. It creates hot exhaust gases moving downward at kilometers per second, forcing the rocket upward in response. Since throwing away mass is the only way to generate thrust, the rocket is trapped by its own changing weight. A rocket becomes lighter as fuel burns, meaning acceleration increases as flight progresses. Tsiolkovsky's equation connects final speed, exhaust speed, and the mass ratio. The math is vicious. Velocity increases logarithmically. Doubling your fuel provides only a small fraction of additional speed. Engineers can try to increase exhaust speed, but chemical rocket engines are limited by the energy contained in chemical bonds. Once you hit those limits, the only way to go faster is to increase the mass ratio. Nature enforces a steep price on speed, demanding exponentially larger rockets for every marginal gain in velocity. To survive these mathematics, engineers cheat the mass ratio. They shed empty fuel sections mid-flight, so the remaining engine has less weight to push. This strategy creates towering, multi-stage structures, where the vast majority of the vehicle's architecture is designed to be discarded. On the Saturn V moon rocket, over 85% of the total launch mass was propellant. That massive fuel system existed almost entirely to push the tiny command module at the very top into its trajectory. This brutal, towering architecture is a direct result of the physics. It is the only physical configuration that survives the mathematical constraints of leaving Earth. These constraints hit a wall of absurdity. Interstellar travel using chemical rockets at 10% light speed requires fuel masses larger than planets. Even small additions to a payload at the top of a rocket ripple downward, demanding more fuel, larger tanks, and heavier supports, which in turn require even more fuel. Escaping a planet is a problem of exponential burden. Every launch is a hard-won victory over momentum conservation, where we sacrifice an ocean of mass just to lift a tiny speck of ambition into the